All right. Homework for today was from week 6, right? And don't let me forget later on to talk about the exam for next week. Okay. So we were supposed to create a fraction class. So at the end of last class, we started dealing with objects. We're supposed to create a fraction class that has 2 private fields. And I said for right now, just assume private's fine. I said we're going to talk about that a lot more today. Numerator and denominator of type big integer. So your fraction can hold big integers. Fraction should be able to display itself. It should also be able to add itself to another fraction, returning a new fraction in reduced form. It should also be able to subtract another fraction from itself, returning a new fraction in reduced form. Okay, so let's go ahead and write that. So let's see here. Do we already have a 535 somewhere? Okay, so we're going to go ahead and we're going to create our fraction class. So we'll right click, new class. And we're going to call this guy a fraction. All right, and kind of just walking through the code here, it says this guy has 2 private fields. That's instance variables, variables owned by the class. One for numerator and one for denominator, both of type big integer, which we introduced last time. All right, so I'm going to have a private big integer numerator, a private big integer denominator, and it's going to want me to import java.math for big integer. Okay, now we need to have our constructor just like we had in our person class. This was our example from the end of last class where we had some private fields, first name, last name, and age. Here's the constructor for building that guy. Notice the constructor has the exact same name as the class. So our constructor is going to be called fraction. Okay, so we'll say fraction, and this guy's going to take in a, we are actually going to, couple different ways you could have built this. I'm going to build it in maybe the more object-oriented, convenient way. I'm going to say this guy's going to take in a integer numerator, well, let's say integer num int denom, because we haven't introduced this keyword yet. All right, and what we're going to do is we're going to go ahead and build big integers out of these guys, storing them up here, kind of making it convenient to use the fraction. So before I go any farther, let me just kind of show you what I mean here. You could have had this guy take in big integers. That's fine. Perfectly acceptable for your homework. I'm kind of just showing you maybe what one of the goals of object-oriented programming is, to kind of hide the details. Okay, remember when we talked about our example over here with the telephone? The pile of wires is the procedural version of the telephone. The object-oriented is the thing that looks like a telephone. So in the big scheme of things, if we say big integers are kind of complexy things, we don't like working with big integers as people, but we like work. You can come in. You're not going to bother me. It's like so timid. just chilling at the door. Yeah, you get your B for the day. You going to let me pay you this week?
We've done lots.
That's on recording too. It is. All right. So if we think about big integers, excuse me, I have like something dripping down my throat. Jeez. We think about big integers. We might kind of think of those as being kind of complexy type things. Ints are nice and friendly to us, right? You pass the number 5, you pass the number 7. Those are friendly type values. But creating a new big integer and passing it the string 7 or something seems to be a little bit more complex. So I'm going to hide the complexity inside of our fraction class so that out here in driver, when I want to create the fraction 1/2, I can say fraction f is equal to new fraction 1, 2, like that. Okay, kind of a nice friendly way of creating fractions where I just have to pass this guy 2 ints, as opposed to passing him new big integer 1. Make sense? This looks a little scarier. Now, my decision here, though, does come with a little catch. The catch is, since I'm taking in something of type int, I am limited on the maximum size of the value I can send in.
Yeah.
Okay? That is limiting me for the size of the initial fraction that I built. Now, if I want to stretch it a little bit, I can come into fraction, and instead of saying these guys take ints, I can say these guys take longs. So now it's plus or minus 2 to the 64th or 2 to the 63rd power for size of the value. Bigger values, but not arbitrary in size. Still, they have a finite value. Okay, but this will still allow me to build fractions like this out here as opposed to having new big integer. Pick your poison is the punchline. But to me, this looks friendlier than the equivalent like that. So these two lines would essentially be creating the same thing. But the second one is showing a lot more details out here. Make sense? So let's go ahead and write that constructor. For fraction, remember, our big integer constructor requires us to pass it a string. So I need to turn num and denom into strings. How do I do that? How do I turn a primitive type like an int or a long into a string? Concatenate it onto the empty string. Yep. So I'm going to say numerator is equal to a new big integer. Okay, this guy up here has no value yet, right? I'm going to give him a value, and he is of type big integer. So I'm going to create a brand new big integer, and I'm going to build it out of this long. So I'm going to say empty string concatenated with num. Like that. So this concatenated with num will end up being the string representation of whatever num is. So in our example here, it'll be a 1. Okay, the string 1. And I'll send that into the constructor for big integer. Similarly, I'll say denominator. I hate that word. It's very difficult for me to spell. Okay, denominator. Okay, I got it. Nailed it. Okay, big integer. And this guy will take in denominator. Okay? Make sense? Denom, thanks. There we go. Now it makes sense. I was testing you. Okay. Now, if we really want to be fancy, I can actually create a second constructor. And I can say, have we talked about, what's it called when you have more than one method with the same name but a different numerator type of parameters? Polymorphism. Okay, so this is an example of polymorphism here. So I'm going to have a version of fraction that takes in a big integer, num, and a big integer, denom. And this guy will just set numerator equal to num and denominator equal to denom. All right, these are two different ways of building a fraction. One of them takes in two longs and creates big integers out of those. The other one actually takes in two big integers and just sets the fields equal to those. All right, so by creating two separate constructors here, I now make both of these legal ways of building a fraction. Not required for your homework. Okay, your homework, either one of these constructors was perfectly acceptable. Okay, or I guess if you really wanted to have one that took in a string and then you use that string to build a big integer, that's fine. Okay, whatever makes you happy. All right, I'm just kind of doing, expanding on our understanding of objects here a little bit as we're going. All right, so we made two constructors here for our fractions. Now we're supposed to have a way for a fraction to display itself, right? So we'll say void display. And a fraction is probably going to look like one half would be 1/2, kind of like we had last time. So we would say something like system dot out dot println numerator concatenated with a slash concatenated with denominator. All right, and we are taking advantage of numerator and denominator, which are big integers, having some sort of facility for making them look like the numbers that they contain. And I don't think we talked about that last time, did we? No, we didn't. Okay, so I will explain today why this works, but it does work. Okay, so historically, if we would have said, since this is an object, like we had random objects before, it would have shown a memory address, right? But in this case, I'm printing out numerator, which is an instance of big integer, and this guy will show he'll show the actual number. It'll look nice for us. And it's because something special is happening inside of big integer to make it work. Okay? So let's go ahead and test this real quick. So all I've done is given myself two different constructors so I can build fractions two separate ways, and then a method that allows each of those fractions to display themselves. So here I built my fraction f the first way. I built my fraction f2 the other way. They're both going to ultimately be the fraction 1/2, right? So now I can say f dot display and f2 dot display, and I can run this, and I get 1/2, 1/2. All right. As opposed to saying, if I say system dot out dot println f, this is going to be the memory address that f holds, the pointer. Okay. That makes sense? So this is what we would typically get for an object being used inside of a println. That is not the case here with our big integer numerator and denominator for a reason that's related to a method called toString. And we'll talk about that today. We will make this work. Okay? We will make system.out.println f do exactly what our display does now. Okay? Heck, let's just do it now. All right, so actually, let me back up here. So let's go to the documentation real quick. All right, and we are going to java.lang. And we're going to go to the original object. Okay, remember when we first started talking about objects, we said all objects inherit from the top level object class, right? Okay, we have a top level dude. We did talk about that, right? Yay, nay, maybe, sort of. Nobody knows what I'm talking about? Oh, we can't trust what she's saying.
Right.
All right.
You pay attention though.
Let's see. Well, I don't know what I just did. Whatever. Yeah, we're missing a bunch of crap, aren't we? Huh. Interesting. Okay. Just draw pictures here. Wasn't important for our homework here, but just to give you an idea. So at the very top level, we have something called an object. Okay? So we have this object class, and that I just showed it to you in the documentation here. So object is the very top level object inside of the Java programming language. In fact, you would find the same exact model across all, let's use that, in quotes, all object-oriented programming languages. You might be able to find some really old, weird ones that follow a little bit different model, but generally speaking, Java, Objective-C, C++, Java, the top level class is called object. Objective-C, it's called NS object. In C#, it's called object with a lowercase o. In C++, it's object. Is that it? I think that's close enough. All right, so there has to be a top of the hierarchy. Okay, now in our example here from last time, person, there's something, remember when we first talked about the evolution of our programming languages when we went from C++ to Java, that Java hides some stuff from us that C++ we used to have to write? Okay, there is something that's up here that we're not seeing. Okay, and that is this, extends object. All right, extends means it inherits from this guy. That is, a person is an object. It gets everything that object has, and then a little bit more, whatever we've defined in here. Okay, so this is something that's hidden from us in Java, but we need to appreciate that it's there. And I'll talk a little bit more about that evolution of those languages today now that we're getting into objects and starting to appreciate what objects are for. All right, you're going to like that one. You're going to like that because you have some C background, right? Yeah. Oh, man, you're going to hate that language now. All right, so anyways, that's their punchline here for us is at the top level we have object, and then what we did is we created a person. We've also created a fraction. Okay, both person and fraction are objects. So they get everything that objects have in them. So in the documentation here, this is what an object is. All right, now way down here, just get to the, here, it's higher up here. Objects don't have much. So this is the, just the base crap that's inside of an object, most of which you will rarely use. But this guy right here, toString, it returns a string representation of an object. Well, if you think about an object being the most generic form of an object, we have to, whoever wrote the object class has to make this guess about what a string representation of a generic glob is. And what they decided is that object that really doesn't have any form, the most generic way we can represent that as a string is by its memory address. Okay, so this method right here, the default version of this, gives you the memory address. Okay, and what I'm going to do here, just to show you, again, more hidden stuff. When I come out here to driver, and I just did a system.out.println f, let me make sure I didn't change anything. Okay, we're good. This is actually calling f's toString method. Okay, so this is my fraction. And there's a method in here called toString. And that's what's automatically getting called, even though this was hidden from us. We didn't see it. Okay? Now notice, we did not write a toString method in here. Correct? We got it from our parent. That guy. He's the one that handed us those methods. Okay? Most of those methods are really, really, really high level. We're never going to need them type thing, but we have to have some original that we can use as a building block for building all other objects. There had to be a beginning. Make sense? Okay, so built into our object-oriented languages, in order to support object-orientedness, they had to create this single entity that is a generic object of which all other things that we're going to build on our own come from. All right? So, right here, f.toString is going to give us the exact same thing if I just said f there. Okay? Same exact output. Why is that? Because the println method knows that if you pass it an object, and let me show you that. Keep connecting the dots here. I'm going to go into, let's see, println, well, let's just go into system. I think it's a print writer, isn't it? Here's out, oh, it's a print stream. So here's our out variable, which is a print stream, system.out. Notice it's a static value. So let's use some of our knowledge here. Static is what? Class method or, well, class field or instance field? Class field. How do you know? Static. How do you call class fields? Using the name of the class in which the field was defined. What's the name of this class? System. So we say system.out. Okay, makes sense? Okay, this isn't just made up crap. Everything is consistent. Okay, so that's why reading documentation helps us. Fields are what? As opposed to methods. What are fields? What are those guys? Yeah, variables. Yeah. A field is a fancy name for a variable that belongs to a class. Okay? These look like variables, don't they? Yeah, they're variables, just like in person. These look like variables, don't they? Now they're fields.
So what's the difference between
It's the same. Okay? Field is an object-oriented vocabulary. Okay? Field is the term for variables that belong to an object. Okay? But these guys are just variables. You'll find a lot of people just refer to these as instance or class variables. Are these instance variables or class variables? Instance variables. How do you know? No static. Instance variables. No static. We don't have to learn new crap. Fields, methods, same exact thing in terms of the static versus no static. Only difference is methods have parentheses. They have parameter lists. Okay? So these guys are fields. This guy's a constructor. This guy's a method. Now notice, what's the difference between our constructor and our method? Okay? And this is something that deviates a little bit from to other languages. In Java, the constructor, this guy right here, the name of the constructor must be identical to the name of the class. Case sensitivity and all. Okay. That is not necessarily a universal rule across all languages. It's true in Java. It's true in C#. I think it's true in C++. It is true in C++. In Objective-C, though, it's not. In fact, in Objective-C, it's extremely uncommon for the constructor to be named the same as the class. Objective-C uses a little bit of, I've shown you a little Objective-C in here, haven't I? Yeah. I've popped it up. Let me just show you a constructor real quick so I can keep connecting these dots. Additional components required. Oh, nice. New magic tricks from Apple. Things are bound to go wonkers now, right? Here, we'll let that cook in the background while I keep going. I'll show you a constructor in Objective-C in a few minutes. If I forget, somebody scream at me. Okay, but Objective-C typically does not name it the name of the class. Either does the newer language Swift, which came out of Objective-C. And I'm going to talk about that evolution of languages today, since we're kind of at that point now. I mean, this whole class up to this point, we're almost done with the course. This whole class has been teaching an object-oriented language Java, and we're just now starting objects. So up until this point, it's been a procedural programming class. Might as well have been using C. Okay? Okay. Let's see that finish real quick. If it's finished, I'll just do it now. All right, fine, we'll do it. I'll open up this real quick. So let's go into this guy. Oh, it's a view controller. I need one of my. Oh, I don't have any of those classes in here. Doesn't matter. I'll just write one real quick. So I'll go ahead and I'm just going to create a new class just like our fractions. Actually, I'll create it like our person. So we'll create a new file in here. This guy's going to be a Objective-C. I see it's going to be Objective-C file. We'll call this guy, what did I say, person? I want to do fraction. Oh, I don't want that either. It's going to be a bad example for you. Give me a moment. There we go. All right. So here's our fraction guy down here. I'm actually going to put everything. These older languages have headers and have a header file as well as the actual implementation file. So the .m file is like a .java file. The header file is kind of some like documentation. So here in the header file, I'm going to say we're going to take in an int numerator and an int denominator. Okay, notice I could copy these lines and paste it right into Java, work just fine, right? Same exact primitives. Why? Because they came from C. All right, I assume we didn't lose that part of our slide set. I wonder what happened to our slides. It's a disaster. Yeah, see, so we got C, and off this came C++ and Objective-C. So we're looking at Objective-C right now, which uses C primitive types, just like Java uses C primitive types. So Java didn't invent the idea of an int. They came from this dude. Okay? So now, when we create our constructor, so I'm going to go ahead and define our constructor down here. Don't try this at home, kids. It's a pretty long constructor, right? When you program in Objective-C, though, you actually get used to it. I think you'll end up, well, many people end up liking it better. All right, so notice the constructor here does not have the same name as the guy here. Also notice inside of .h, our fraction extends NSObject. Objective-C does not hide it from you like Java does. So this is how inheritance works in Objective-C. That is, that guy right there is equivalent to the word extends in Java. And we'll look at some inheritance today. But I'm trying to give you that hierarchy model that above everything is this idea of an object in Java. Above everything is this idea of an NS object in Objective-C. And we talked about, when we were talking about this slide, the whole thing where Steve Jobs got fired, came back to Apple when they bought Next Computers, and what we know of as Apple today is actually Next Computers with an Apple logo. Mentioned that? Okay, well here's more proof right there. NS, next step object. Okay, this is a brand new iPhone file right here for creating an object. I mean, this is not old stuff that's not being used today. If you created a brand new iPhone project today, it would look like this. Okay, so constructors in Objective-C tend to be very verbose. So if you look at our constructor for fraction here in our Java program, the name is fraction, and it takes two parameters, a long and another long. We happen to name this guy num and happen to name this guy denom. So hopefully, based on the name of the variables, we understand that, oh, it means the numerator and the denominator, right? But what if we had named these guys A and B? It would not have changed the meaning of that constructor, but it might be a lot more difficult for us as a programmer to look at it and know what it means. I know I need to give it two longs, but what do the longs represent? Do I give it the numerator and the denominator? Do I give it the denominator and the numerator? Do I give it just two random numbers of my choice? What is it meaning? What is it wanting from me? Okay, that's why you want your variables to have decent names. Well, when we look back here at Objective-C, through its verboseness, tends to be clear. We're going to initialize a fraction, that is init with numerator. This is all just like a comment. Okay, init with numerator, give me an int. And denominator, give me an int. Okay, so it spells it out for you. That makes sense? And then somewhere else, if I were going to, here, let's, I'll just create a quick fraction. Init with numerator 1 and denominator 2. So here's an example of creating a fraction in Objective-C. Fraction f. Right here, that's like the new keyword. Allocate memory for a fraction, then call the constructor init with numerator 1 and denominator 2. Okay, same exact crap, just a little bit different syntax, but I would definitely call Objective-C a more archaic language. Okay, we'll swing back through, pun intended, we'll swing back through in a little bit and I'll show you the Swing programming language. Get it, the pun intended thing? Swing is the new language. You've heard of Swing? Swing, Swift. Swing's a real language too, though. It's not what I meant to say, but at least my joke holds up. Swing is a Java API for graphic user interfaces. But I'm talking about Swift. Swift. Okay. So in any case, that's some Objective-C crap. I'll leave it up here for now. I'm not using it in any place. All right. So in any case, that kind of gave us an idea of how other languages are doing the same thing. Actually, one more thing I can show you. Notice here I have a little dash before this guy. Instance method, class method. Objective-C, as opposed to Java that says it's a class method if static's there, it's an instance method otherwise if static's not there. In Objective-C, instance methods are preceded by a hyphen, class methods are preceded by a plus. Same exact meaning. Same exact meaning. If I want to call this guy, what do I do? So maybe inside of here. So this guy's a class method, right? How do you know? The plus sign. How do I call class methods? Using the name of the class in which it was defined. Here's the name of the class fraction. Here's the name of the method. All right, so Objective-C uses this notation instead of fraction dot another gen. It's called message passing notation. Not important, but understand that this is a very different looking language, but the exact same crap exists. Say, if I was teaching you an Objective-C course, we'd be talking about the exact same stuff. Okay? All right, so I got my two constructors. I have my display. We were just looking at the documentation here. We saw that print stream, our out variable, is of type print stream. It's a static variable, so system.out to get us to that. And we're going to look at print stream. We're going to see there's a whole bunch of different versions of println in here. There's a bunch of prints, and here's all our printlns. All right, and what's it called when you have more than one method with the same name but a different number and or type of parameters? Polymorphism. Notice one of these guys here takes in a generic object. Okay, so this is like your catch-all println. So println has a version for all the primitive types. So this is println, just kicks it down a line. That's like calling println with the empty string. Here's one that knows how to print a Boolean, a char. Here's a nice convenient one for printing out a char array. Okay, because char arrays are kind of like strings. One that takes a double, a float, an int, a long. So all of our primitive types, except like not short and byte, because those are just ints that'll cast. I don't know why they didn't just make one for long and just take care of all the primitives, the int primitives. Doesn't matter. Then we have one for strings. Okay, because strings, when we print out a string, we kind of know there's an understanding of what a string should look like. It should look like the contents of the string. Hello, or world, or cat, or dog, right? All right, well, let's say I have an object called airplane. What should println do when I say print an airplane? Well, that's what it does do. But from a human being, one person to another, what would you expect to happen if you said print? I have an instance of an airplane here called the airplane. Print that out. What should it print? Kind of doesn't make sense, right? It's like, okay, well, an airplane means a lot of different things. It's kind of a thing. It's not something you print. Although that's kind of changing now with the 3D printing, right? Before long, we will be printing airplanes. But the punchline is this is our catch-all. There's a version of println that just takes in generic objects. And what this guy does under the hood is he calls that object, so in this case x, he calls x's toString method. Which by default, he's guaranteed that guy has a toString method. Why? Because the object class this guy has a toString method. And that's guaranteed to be there. People who wrote Java made that guy there. So all objects come with a toString method, whether you add your own or not. They inherit it from the parent. So that println method can just go ahead and, with full confidence, call whatever object is passed to it, call his toString method, knowing full well that it'll at the very least call this one, the one it got from object. Okay? And I'm telling you, in those situations, because there's literally an infinite number of objects, because we can create our own. These aren't just objects built into the language. We can create our own. So for these objects that we're creating our own, the println guys couldn't have known what our objects look like and what they should look like if we were to print them. So they had to have some sort of common ground. So objects toString method says, here's the memory address. If that's not good enough for you, you can rewrite the toString method yourself to make it look like something else. Okay? So that's where we get up here. And here, notice you can see this hierarchy here. Here's a print stream, which is an output stream, which is which is a filter output stream, which is an output stream, which is an object. This is that hierarchy. So print stream has a parent filter output stream, has a grandparent output stream, and his great-grandparent is object. That makes sense? That's the hierarchy for this guy. So even though there's a whole bunch of generations between him and the original object, anything that wasn't redefined in these guys is still left over. Okay, so here in original object, we have that toString method that returns a string representation of the object, which by default is the memory address looking thing. Okay, so what that means is when we go into our code and we say system.out.println f, f is an instance of fraction, it's going to go into our fraction and say, is there a toString method in here? There's not. So it's going to go up a level to our parent. Who's our parent? This guy. It's going to say, do you have a toString method? In this case, it does. So what's it going to do? It's going to print out the memory address looking thing because that's what object's toString method does. Now, we can choose to write our own version of toString. And now when I run this, it says woot. I changed nothing inside of driver. All I did is create my own more local version of the toString method, which does what's known as shadow the one I got from my parent. Because the one I got from my parent's still there. I can say woot concatenated with super.toString. Okay, we're getting a little ahead of ourselves because super is how we refer to our parent. So just let me slide with this for right now because we're going to be talking about that a lot today. And now we get woot as well as what our parent did. Okay, so this is kind of proving that lineage, proving that that connection. All right, but for our assignment right now, not important. So let's actually get through this thing. So we have a display method, displays numerator and denominator. Oh, I'm just taking it back to where we were.
Why is the super here?
Huh?
The super here. What is
I'm not going to tell you yet. You will. I'll tell you today. I promise I'll tell you today. I already said what it is. You weren't listening.
I mean, yeah, I hear.
It's how he refers to his parent. It's how an object refers to his parent. So in this case, object. We'll be talking about it in detail today. So notice I just made toString work just like display, except this guy returns the string. So now in driver, when I print out a fraction, it'll make it look like a fraction. There's my fraction. That was system.out.println f. Because it called f dot toString, which returns the thing that looks like a fraction now because I wrote it to do that. Make sense? All right, so that's what that generic object version of println does. It calls whatever object you passed it, calls his toString method. And I'm writing a more local copy of it because fraction is an object, even though you don't need this. And notice I left that in there and it was perfectly legal. Right? But you never need that in Java. It's assumed. So this goes back to the very beginning of this course when I was telling you how Java hides stuff from you. And that's good once you know what it's hiding. But if you just rely on the fact that, oh, that's just how it's always been, you start losing that connection to see where these things, how the logic flows. Okay? So I'm going to take toString out for right now because that wasn't part of the assignment. So we have our display method that shows a fraction-y looking thing. Fair enough. Let's see, what else were we supposed to do? Add and subtract fractions. Okay. So we're going to have a method here called, that's going to return a fraction called add. That'll take a fraction as a parameter, and it's going to add these guys together. That is, it's going to add f and this particular fraction's numerator and denominator. All right, so first thing I'm going to do is I'm going to say big integer common denom is equal to, denominator dot multiply f dot denominator. So I'll multiply my two denominators together. Okay, that gives me my common denominator. Then I'm going to get my new num1, and this is going to be numerator dot multiply f dot denominator. Then I'll have big integer new num2 is equal to numerator dot multiply denominator dot multiply f dot numerator. All right. Now we can build our new fraction. Correct? So now we can say fraction, new fraction, is equal to new fraction. Notice I ran these together, so don't let the new word here mess you up. And the fraction we're building is the one that has a numerator, new num 1 plus new num 2. And the denominator, common denom. And then ultimately we will return new fraction. We're not reducing yet, but this should build us a fraction. All right, so we're gonna, so let's just go ahead and call it real quick so we can see how this works. So I have f and f2, and we'll say f dot add f2. And that guy's going to return a fraction, so we'll tell that fraction to display itself. Okay, so f is going to call his add method, and we're going to pass in as a parameter f2. So inside of here, whenever I say numerator, I'm referring to, in this particular case, f's numerator. Whenever I say f dot numerator, I'm referring to this f's numerator. Okay? So f from out here is this guy in here. F2 from out here is this guy in here. Right? I'll make that a little easier after we go through this part of it. Okay? But this is what you knew how to do for your homework. So this is going to create our common denominator by multiplying the two denominators together. It's going to get two different numerators. One multiplying this guy's numerator to the other guy's denominator, and the other one multiplying this guy's numerator. Hold on, this isn't right. I was testing you and you failed. It's going to multiply this guy's denominator by the other guy's numerator. So that's our cross multiplication, right? Then I'm going to build a brand new fraction using my constructors up here. The one I'm using here is the big integer one. And I'm going to add new num 1 to new num 2. These are both big integers, and that will produce a big integer. And then pass in common denom. So this will create a brand new fraction, in this case called new fraction, and then I'll return that as a fraction. All right, class method or instance method? Instance method, how do you know? No static. How do we call instance methods? Using instance of the class in which the method was defined. In this case, it's fraction. So out here I have two fractions, f and f2. So I can say f dot add f2, say display. I can also say f2 dot add f. I just called it f. But make sense? These will have the exact same result, but the difference is on this call right here, f. So this is driver f and driver f2. That's how I'm going to refer to them. Okay, this is driver f and driver f2. Inside a fraction, driver f will be these guys. Driver f2 will be this guy. In the second call, driver f2, driver f, driver f2 will be these guys. Driver f will be this guy. Because in that second call, driver f was the parameter we passed in, not the guy who called his method. All right? So understand these guys will, in this case, give us the exact same result, but we are calling the other guy's method. This first call, we're calling f's version of the add method and passing f2 as the parameter. This one, we're calling f2's version of the add method and passing f as the parameter. All right? So we will get these guys added together. 1/2 plus 1/2 is 4/4, so it's kind of a stupid example, but let's switch it to a fourth just to keep ourselves somewhat sane. All right, so there's our 6/8, not reduced. All right, Now we're going to teach our fraction how to reduce itself. And we could have done it in there if we wanted to, but I'm going to go ahead and write a generic reduce method because we're going to need it for both add and subtract. Okay, so we're going to go ahead and we're going to say void reduce. Because reduce is not going to return anything. All it's going to do is adjust the fraction that called its numerator and denominator. Okay? So, big integer, we learned about GCD last time. Big integer has a GCD. So first thing we'll do is say big integer, the GCD is equal to numerator dot GCD denominator. And then we'll say numerator is equal to numerator dot divide the GCD. Denominator is equal to denominator. I hate that word. It's like my kryptonite. All right, so we'll just divide both the numerator and denominator by the GCD. And that's it for reduce. So reduce is just going to figure out what the greatest common divisor is of both the numerator and the denominator, and then divide the numerator and denominator by that value. And we're updating the fields owned by this particular fraction. So what I can do here now in add is when I go to return my new fraction, before I do it, I could say new fraction dot reduce. Class method or instance method? Instance method. How do you know? No static. So how do you call instance methods? Using an instance of the class in which the method was defined. So we need an instance of the fraction class, and we just happen to have one right here. I built a new fraction. This is where he's being built right here. And I told him to go ahead and reduce himself. And then return. And now when I print it out, we'll see the reduced version of those fractions. Make sense? All right, so that's add fraction. Let's steal this for subtract fraction. Subtract, we still need a common denominator, right? Okay. Then we're still going to get our numerator, new num, and new denom, right? Okay. Okay, instead of add, we're going to say subtract. But you need to make sure you're subtracting the first one from the second one. Okay, I had somebody ask me whether or not you should figure out which one's the smaller and the larger, but no, it's whoever called. So if I say f dot subtract f2, I am subtracting f2 from f, giving me whatever the result is. If that's a negative number, fine. If it's a positive number, fine. Okay, so that's subtract. Go back out here to driver. And let's go ahead and say f2 dot subtract f1 dot just f dot display. And we get our negative 1/4. Make sense? All right, so that's a reasonable solution to the homework assignment. Questions about that?
Can we make those two functions, add and subtract, just in one to make it more efficient?
Just in one to make it more efficient? Okay. So because we notice that add and subtract are both using all the same crap, except this thing right here.
So just send the operation.
Yep. So one thing we could do is
Then we'll take string, and from the string we can know what operation we do add and subtract.
All right, so you would just say, maybe call this math, and it would take in the fraction as well as the char op or something like that, the operator. Yeah, you could. I guess I think it maybe doesn't make.
Does that have effects on the performance of the program?
The memory footprint maybe a little bit, just because we're repeating these, these 3 lines of code, and then these 2 lines of code every single time that we call these methods. So you get a little bit bigger footprint having 2 separate methods like this, but it's also very much object oriented. This is how we subtract, this is how we add. If you really wanted to have a helper, what you would do is you would say something like, it's not going to work either. I mean, you could create another method that has these lines in it, and then depending on whether or not it was add or subtract, you could pass in that, you maybe have an internal method here like this. That's like fraction, do math. Let's do maybe, in this case, big integer, A, big integer, B, big integer, C, just because I don't want to give it long variable names, and then a char op. And then what you would do in there is you would basically do these lines. You would say if op is equal to plus then else. Something like that. And then what you can do is inside of actually we could do this. So you could do something like this where you have this little internal function called do math where you pass it the fraction and the operation you want to do. It does all that common stuff in here, creates a new fraction. If it was addition, it does the add. If it was subtraction, it does the subtract. Then it reduces and it returns the fraction. Then inside of subtract and add, you could just return do math F. and the char minus. F and the char plus. So subtract and add are written in terms of this function that we wrote here. I would probably write it the other way we had it. Technically, this is a little bit more efficient, just a little bit. Actually, it's not as efficient. It's a toss-up. This way is more memory efficient. The other way is more performance efficient, because in this one we're asking 2 extra questions. We're asking, was it a plus sign or a minus sign? So this particular way is technically going to take more instructions. Okay, it's going to take longer to do. The other way will just have a bigger memory footprint. So I guess pick your poison, but I think the object-oriented version of this would look like this. Very compartmentalized. This is how we subtract. This is how we add. Make sense? Okay, so now that we have that, I want to talk about a couple of things here. We're going to kind of swing back through and look at a few things. Specifically, the idea right here. I don't like the fact that I had to name my parameters in fraction num and denom. We already looked at Objective-C and we saw how verbose the constructors are there. We want to be very explicit. We want to say, this is the numerator. This is the denominator. Make sense? We want to be very explicit about that. But then we run into problems. And that is, so I'm going to change this to numerator. All right. Variables always resolve to their most local definitions. Correct? So when I say numerator right here, what's the most local definition of numerator? This comes down to variable scoping. Is it this guy or is it this guy? This guy right here. This constructor is like a method. That method has its own scope. So what I have highlighted in blue, that's the first variable scope that we will check when we're resolving all variables. Remember we had that slide that we had the different color backgrounds and stuff on? It's possibly a lost slide now, but whatever. But in any case, see, something went wonky with iCloud earlier this week. And I had to remove iCloud from all my machines and put it back on. My calendars were messed up or something, and it seems like maybe some old wherever the break happened, the mental break in iCloud, that's the version of the slides. So I guess it just is what it is. What was he doing? Actually, I might have. Let's just see if this happens to be more complete.
Who sent us?
At the very least, this one has a lot more stuff in it, right? Okay. So somebody remind me at the near the end of class when I'm talking about the exam, I'll email this to the whole class just so everybody has it again. I think I did it once, but just in case. Because this covers pretty much everything except what we just started talking about today. So what I'll do is I'll add stuff to my broken slide set, and I'll export that, and I'll send you the broken slide set with the new stuff, and this old slide set with the old stuff. And between the two of them, you should have all your crap for the exam, and anything that's not on there, you'll just get a 0 on. Fair? It's actually quite funny. I do some mentoring for developers around the world. I have about 12 students, and one of my guys is he's a programmer at Google. So I'm teaching him the Python programming language. And so I kind of keep it's for a company called Thinkful. So I'm just one of their professional programming mentor people thing. I do web chats with folks is what I do. But in any case, I have like a single slide set that I use for all of them. So I just keep adding crap to it. So when I'm talking to one person, I might be talking to a guy who, the Google guy lives in Ireland or Scotland. Ireland. He's in Ireland. I'm like, have you seen this slide? Have you seen this slide? I just come flipping through them, and they're all over the place. It also gets me all messed up because I'm programming in so many different languages during the week, and I'll be talking to one guy, and I think he's doing iOS and Swift, but he's actually a Python student, but I'll be showing him all the stuff in Swift.
How many languages do you teach?
A lot. See, I teach Ruby, Java, Objective-C, Swift, Python, Node.js, which is actually JavaScript. Did I say Objective-C already? Objective-C. I don't have any C# students, but I do C# with our software engineering guys. It gets bad. See, wouldn't that be pretty impressive if I spoke that many languages in real life? I'll be sitting there and I start like moving into another language, and the compiler starts, the IDE starts yelling at me. It's like, this is Eclipse, you're writing in Objective-C, not going to work, not going to work, not going to work. And then some of the languages are wonky, like Python doesn't have curly braces. Instead, everything's done through indentation. So instead of having curly braces here and here, you would just know this was part of this constructor because it was indented. That's a thing. Okay, so anyways, back to reality. So I want to name my constructors something that's meaningful, right? So I'd like to call my numerator, numerator, my denominator, denominator, which just happens to be the same name as my fields, okay? Because I named them something meaningful. So I need to have some way of differentiating between these guys and these guys, okay? And we have a very special keyword for that. Not super. This. We have something called the this keyword. Very, 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 keep adding very important. Just like the top level object in object-oriented languages is a very important concept to understand how that hierarchy works, the concept of this is extremely important. So I'll define it first. So I'm going to say this is how an object refers to itself from within itself. Okay? Now let me give some meaning to that through an example. Okay, so this is how an object refers to itself from within itself. Back here in code. In driver, when I said f.add, f2. Well, actually here, let's just look at the constructor. We'll deal with this guy right here. Okay? Out here, I'm creating a fraction called f, correct? And that fraction is going to be a new fraction. Here's my call to the constructor. And I'm passing in 1 for numerator and 2 for denominator. I have a local variable. This guy's going to be called f, correct? He's going to be called f. So using our nomenclature before, this is driver f. Okay, this is driver f. When I'm inside that constructor, though, I no longer have a variable named f. Inside this constructor, driver f is known as this. This is how an instance of an object refers to itself from within himself. Out here, I have access to that variable f. So I can say f.add, f.display, things like that. But inside this constructor, this variable name is not in scope. I don't have access to a variable name f. But I still might want to talk about my own things, my fields, my numerator, my denominator. So inside of that constructor, inside of the fraction class, the particular fraction that's being built right here is known as this. Okay? So I would say this dot numerator, this dot denominator. I want to set my field called numerator equal to a new big integer built from the numerator you just passed in. I want to set my field called denominator equal to a new big integer built from the field or built from the denominator you just passed in. All variables resolve to their most local scope, most local value. Numerator here will resolve right here. Denominator here will resolve right here. And you can even see the orange color. See how they color highlight each other? Okay. But this dot denominator, this guy right here. See, that's eclipse breaking. Eclipse actually thought it was this guy, but it's not because it's only highlighted this part. When I say this dot, notice it's that guy here. This dot is saying, inside a fraction here, this is how I refer to myself, the fraction being built. I'm saying, set my denominator, the guy that belongs to this instance. This guy is an instance field, right? How do you know? No static. How do you reference instance fields? Using an instance of the class in which it was defined. So I need an instance of the fraction class. Do I have an instance of the fraction class in here? I do. It's called this. That make sense? It's called this. Now, I'm going to show you something back in our Objective-C thing, because this is another hidden magic trick of Java. Did we ever define the this keyword anywhere? It just was magically there, right? So let's go back to Objective-C. So here's our constructor. And I wrote this constructor very much like a Java constructor, but I actually left some very important things out. If I tried to run this, see the build fails. This isn't correct yet. In Objective-C, it's not called this, it's called self. Self is how an object refers to himself within himself. Okay? They mean the same thing. This self. All right? Visual Basic, it's me. Okay? Visual Basic, the way an object refers to itself is the keyword me. C# is this. C++ is this. C, what do you think it is in C? Trick question. Trick question. This is how an object refers to itself from within itself. What do you think the equivalent is in C?
Is there an object?
There's no objects in C. It's a procedural language. Just wasting my breath up here, people.
I mean, C, structs is kind of equivalent to object-oriented, except there's no inheritance in C, right?
True, but not true, but yes, and I'm going to talk about it right after I do this. I mentioned earlier that I was going to talk about that evolution. Now she asked the right question, okay, about structs. Structs are really where C breaks, okay? And I'll explain it. It'll make sense. You've had some C? Okay, you'll agree with me when we're done. All right, so in Objective-C, we have to give value to self. Java does it for us behind the scenes. So in Objective-C, we would say self is super init, that's calling our parents constructor, and then at the end, we always return self. Okay, now what I'm telling you is in Java, or rather in Objective-C, every constructor you ever write will always start this way and will always end this way. If it always starts the same way and it always ends the same way, Doesn't it make sense for it to write it for us so we don't have to?
Yeah.
Okay, that's what Java did. Make sense? All right, Objective-C though makes you write it. They're actually, when I say it always starts this way, depending, in this case, we are only one level of abstraction away from NSObject. But let's say we were, let's say NSObject was our great-great-grandparent. Okay? If NSObject was our great-great-grandparent, which means that we're actually inheriting from something right above us. Maybe it's called, I don't know, dark fraction or something like that. I'm losing my example here. But then we might call upon our parent's constructor rather than NSObject's constructor. And it's possible that our parent's constructor might not just be called init. It might be called something like init with blah 12 and that kind of stuff. So this part of the line could change a little bit depending on whose constructor we were calling. But the default thing would be the default constructor for NSObject is the one that takes no parameters and just builds a generic object.
What happens in Java in this case?
We'll see it when we talk about inheritance today. Okay, Java can call its parent's constructor too by saying super, 1, 2, something like that. I can do that in Java. But you can't say super dot super dot super. You can't do that. You can't climb the tree. All right, so Objective-C always requires us to do this self crap like this. Okay. Java, I'm telling you, it's there. Somewhere up here we have this is equal to new object. And then down here, we're returning this, or something along those lines. Okay? And this is what differentiates a fraction from a generic object. Because all these guys are objects. A fraction is an object, so this, when we first start off, will be a generic pointer to an object. Then we make it special. Now he's a fraction, not an object. That's what differentiates our fraction from an object, the fact that it has a numerator and a denominator, right? And then we'll return that pointer to our fraction. And just to show you this, the proof here, I'm going to go ahead out here and I'm going to say system.out.println this. Okay? System.out.println this. And then out here, I'm going to get rid of a bunch of this crap real quick. When I build a fraction, the one that takes in 2 longs, that constructor is going to take in 2 longs here. It's going to do what it did before, and then it's also going to print out the value of this, which will be a pointer to this fraction. All right? This is inside the fraction class. I'm going to come back out here. Actually, I need to make sure we don't have a toString right now. Okay, we don't. Good. So out here, I'm going to say system.out.println f. So I'm going to print out the value of f in here, where we have access to f. We're also going to print out the value of this inside. Those guys should both point to the exact same place. They should be the same value. This is how f refers to himself from within himself. Okay? I'm printing out this here. I'm printing out this here. So this will, when I call the constructor, we're going to see this printed out. Then I'm going to print out f, and we're going to see they're the exact same value. Okay? They are synonyms for each other. Make sense? Here's the value of this. Here's the value of f. This was how f referred to himself from within himself when we no longer had access to a variable named f. The pointer was still there. This object still lives in memory. Okay? But we don't have access to this f variable that pointed up there. Instead, we had access to this variable called this, which pointed up there. All right? That makes sense? All right, so this is a very, very, very important concept. All right, because we're going to use it very often. Now, having said that, this becomes a difficult thing to teach because it's hard to explain this without saying this a bunch of times. Let me show you an example down here where we were calling our let's do it in here. So in my constructor, I have a method called display down here, right? Display is a class method or an instance method? Instance method. How do you know? No static. How do you call instance methods? Using an instance of the class in which it was defined. This is defined inside the fraction class. So now I'm going to come into our constructor here, just taking advantage of this, and I'm going to say display. And it's going to work just fine. Okay, and I'll tell you why here in a second, and then I'm going to tell you why you should never write it like that. Okay, so there's my call to display, and then here's my printing of f again. This is absolutely 100% correct. There's nothing wrong with that, and you will find it written like that all the time. All the time. Similarly, for those of you who are getting a lot of help from Google on your old homework assignments, you know, if we had a method static do something, and let's just say this guy prints out. Oh, this is going to be static void do something. And we'll say this guy prints out hello world, like that. Class method or instance method? Class method. How do you call it? Use the name of the class in which the method was defined. So we say driver dot do something. That'll work as well. Okay? And a lot of you had stuff like that in your code. Okay, I'm going to explain this. So first of all, here's our 1/2. So we saw it worked without the instance, and we see our hello world. We saw it worked without our driver dot. This method right here is a static method, correct? That means everything that's happening inside of this is happening from within a static context. Okay, that's what it's called. It's from within a static context. Anything that's called within a static context will have the name of the class dot assumed to be on the front. Okay, so driver dot is there even though you didn't have to type it. Similarly, in fraction, we don't see static here. Constructors are a little bit different animal, but no static, so it's a instance context. So this guy is from within a, let's say, a non-static context. Okay, non-static contexts will always put this dot on there. Okay? You will find many programmers, if not even most experienced programmers, doing it just by saying display or just by saying do something. There's nothing wrong with it, but it kind of falls into that same category as my comments dealing with the opening and closing curly braces with if statements and loops. It's never wrong. It's never wrong to be explicit about what you want. It also reduces your chance of having spelling errors with an IDE. For instance, if I come up here and I type driver dot, it'll spell it for me. I didn't have to type out the whole do something. Okay? That's a convenience, right? So while you were trying to type less by saying just saying do something, you actually open yourself up to potentially having errors. Similarly, if I say this dot, there's my display. Same exact thing. All right. Now, part of it is that convenience factor. Okay, that you don't make errors like that. I also like being very explicit when I program. One thing is it reinforces your knowledge of how things work. There are so many programmers that I work with that it's fair to say they are advanced programmers, okay? But they think they know things better than they do. And part of it's because some of the things they do because they know it works, not because they know why it works. Does that make sense? Okay? And I think that's an important distinction. So, I'm not the best programmer in the world, but I'm pretty good. And if I'm going to take my time to put the extra crap in there when I'm a slob at home, I'm not organized or anything. So if I'm picky about stuff like this, I feel like that should mean something. Okay? If I'm going to take extra time to make my code a little bit more organized, stuff like that, when I don't do any of that in real life. Okay? That means it must be important at some level. And the funny thing, did I mention the thing about Swift, how Apple agrees with me last time? Yeah, with the opening, closing curly braces? Yeah, that's right. I was very happy when I saw that. So, I don't care what you do. If you don't want to use this because you know that you don't need it, that's fine. I mean, if it's right, it's right. But I encourage you to only take shortcuts when you're very comfortable with why you're able to take the shortcut. Same thing when we talked about the plus plus and the minus minus. Having it inside the same line. For instance, let's do that. Did this just break my fraction class? I put the plus plus right here. Am I going to get different results than I had before?
Here's the string, right? So when you put plus in the string, that means...
Well, but I'm attaching it to this guy right here. Is it fair to say that most of you, at least, are unsure? You're not quite sure what this is going to do, right? I've added something to it. It has to do something bad, right?
Yeah, that's interesting.
Okay. Nothing changed. Why? Numerator is a local variable. Resolves to this guy right here, right? When I say the plus plus after it, I'm going to get the current value of numerator right here. Then I add 1. And I never actually use numerator again down here. So sure, it started off as a 1. It became a 2, but I never used the 2. So this did not break it at all. Okay? Punchline there is I would say never do something like this. Make sense? I know exactly what the behavior of this would be. I've done this for a long time. I would never write something like that. I would always take 2 lines. Nobody's impressed if you're able to squeeze more stuff onto 1 line, because you're not the only one who has to look at your code. Make sense? Be explicit. People who look at your code will thank you. All right, so I'm not a fan of shortcuts when it comes to programming, because especially when you have these nice IDs, you actually save yourself time by saying this dot or driver dot, because it'll spell the crap out for you. And it'll tell you what parameters it takes. And you can tab through the parameters to put them on. It makes it, you type less by putting this dot or driver dot in there. You end up typing less, as long as you're taking advantage of the IDE like Eclipse. Okay, well now wait a minute. What about that? Right off the bat, this just looks creepy, doesn't it? Now we got 2 over 2. Because the plus plus was before, it changed the value of numerator first, then concatenated it onto the empty string to build our big integer. This happened right away. Then we concatenated it onto this. That's where, so it became a 1 became a 2 immediately. Okay? And this just looks stupid. I mean, it looks maybe like a little bit impressive or something, but no, I mean, you guys have dealt with this. As you're going to look it up your homework on Google, don't you want the other people's programs to be as easy to read as possible? Okay, when you get some, there's some person who's got some old C program that you're trying to manipulate to work the way you want it to work, you're not getting anywhere because it's like, okay, well, this guy's taking all these little shortcuts. He's got pointers to this, that, and like, well, why can't you just write it in Java? And write it in easy, dumb people Java, right? Don't give me this, I've been programming forever and ever and ever. You should be impressed. And this is called job security, that you can't read my code. Although there might be some truth to that. You write code that nobody else can manage, you probably have a job. Well, you fired me, what are you going to do? It's like my entire program's encrypted. I use one of those old things I pulled out of a Cracker Jack box, the code rings, and code all my variables. I actually had a professor like that in undergrad. He was, and it must have been bad because it sticks out to me. I remember standing up in front of the room. We were learning. We were learning C, and he was saying something to the effect, and I was like a 12-year-old, and he was saying something to the effect of, it's like, well, I'm a real programmer, so we use Gothic variable names or something like that. I've sat up here and I'm trying to tell you that use variable names that are meaningful, right? If you're going to store your name, name your variable name, because that's what you're going to put in there. Don't name it some random word and say, well, I'm going to remember. Like, so you was putting Gothic variable. I don't even know what that means. Maybe, I don't know, whatever. But yeah, he was presenting it to us like it was cool. I just don't get it. I don't get it. All right. Struct stuff, right? All right, so let's talk about the C evolution. Do I still at least have my list of languages? Yep, here we go. All right, so remember we talked about object-oriented versus procedural programming languages, right? We had our example of the telephone over here. Telephone, pile of wires, but the public interfaces are still there, but you had to kind of fish through all the details until you finally figured out, oh yeah, this is a phone. Then you have the object-oriented version of that guy, which has all those wires, but stuffed into the box. Like, okay, they're working. We're not going to need to touch them again. So put them in there. We're going to close it up. And you're never going to get in there again. We've glued it shut. Okay, this phone breaks, go get a new phone. Okay, and then only the public interfaces of it are exposed. The things that we actually need to manipulate it, right? Okay, just like our fraction here. Our fraction has all these details hidden inside of it, right? All this code. Out here in driver, what do? We create a fraction. We can say f dot add. We can say f dot subtract. We can say f dot display. Every one of those methods has a bunch of details behind the scenes, but when we call them, they're easy to use. So I can say fraction f2 is equal to new fraction 5/14, and then I can say f dot add f2 dot display. Oh, I drew my fraction instead of wrote my fraction. There we go. That makes sense? So I created two fractions. I told them to add themselves and display the answer. A lot of crap is happening here, right? But it's not scary like what's happening in here. This is all the details. Okay, once we get that working, we don't want to look at it again. Like, okay, this works. So now we can just use our fractions because we know they already function. Make sense? All right, so this goes back to how human beings solve problems. Human beings solve problems in terms of our memory, asking questions, and repetitions. Repetition, right? The job of a programming language, any programming language, is to mimic the way human beings solve problems with the ultimate goal of telling the computer what to do. If we solve problems in terms of memory, asking questions, and repetition, the programming languages we write want to give us tools that allow us to leverage the way we solve problems. Okay, that's the job of a programming language. So at the top of our tree here, we're going to say that the first modern-ish programming language to try to do this is C. Okay, there were languages before C, but C is kind of has proven to be the source of pretty much all of our modern languages. Okay, so everything up before C kind of was an evolution until we kind of congregated into this language called C that a lot of people adopted. Whether it's the language is extra good or the timing was right because that's when programmers were having to write a lot of programs, whatever, C kind of became this like gold standard for programming languages. So everything we have today is in some way a evolved form of C. All right? So when they wrote the C programming language, they were trying to meet those goals. How do human beings solve problems? Well, they have memory, variables. They have the ability to ask questions, conditionals, and they have repetition. So we're going to throw loops in there. Okay? So we look at C evolution. Well, this guy supported variables. So a variable, a single value of a specific type stored in a named container. Okay? Sounds pretty legit. That'll do what, that's something we still find useful today, correct? They also supported arrays. Well, what's an array? Store multiple values of the same type within a single named container. Okay? It had those guys. Now, we even saw this last class last week we were using arrays to represent fractions, right? So we used bucket 0 was the numerator, bucket 1 was the denominator. Arrays weren't built for that, but we leveraged it, right? We went out to Target, we bought the little organizer thing, and we decided to put some stuff in the first part of it and some stuff in the second part of it. We just remembered what we put where. Okay, so we leveraged arrays to solve that problem. Now, C also had something called a struct. Okay, now let's look at that real quick. Well, let me give a definition first, and I'll show you what a struct is. So a struct allows us to store multiple values of varying types within a single named container. All right, so that's what a struct is. And actually, for those of you who are going to go on and take the 537 class, which is the hard version of this class, we just keep going. It literally picks up where we finish in here. So you should all take it. It's a good class. You've had enough? The programming's so fun, isn't it?
Yeah. You're a great teacher.
Oh, of course. Every morning I wake up, I look myself in the mirror, I say those exact words. Then my wife walks behind me, what the hell are you doing?
Trying to persuade yourself.
I don't know. I have too much fun with it, I think.
But once you know what happened,
Yeah.
you know it's here.
Doesn't it seem like I'm too animated for a programming teacher? Like, this stuff seems like it should be dry, right? What's this?
For a computer teacher of any kind.
Yeah.
Hey.
There's something not wired right.
Hey.
Oh, come on. We all know that I'm cooler than Dr. Locklear. You could ask him. He'd admit it. But he's way more organized than me. Professor Wall's in the middle. You take the average of all of us in the computer science department, we're almost a normal person. You know, me plus Dr. Locklear equals Professor Wall. It's kind of a normal Joe, you know. All right, so anyways, struct. Store multiple values of varying types within a single name container. Kind of let me give you an example of that from a fraction perspective. So I'll just throw another slide out here. Okay. So for instance, C would allow us to create a struct called fraction, let's say. And inside here we can say int numerator, int denominator. And then we can create instances of this guy. Well, actually it's not instances of this guy because structs are actually defined as primitives. But I would say fraction f dot numerator is equal to 1. F dot denominator is equal to 2, something like that. Make sense? All right, so structs kind of allow us to pull off what we were trying to do last week with arrays, but in a way we don't have to remember that bucket 0 was one thing, bucket 1 was something else. With structs, we keep the names. F dot numerator, F dot denominator. I can then create a fraction F2. F2 dot numerator, F2 dot denominator. Set the values. Okay? So structs allowed us to hold, this is all dealing with memory. It allows us to hold values of varying types where arrays have to all be the same type. We can kind of hack that with arrays a little bit by maybe storing everything as a generic object inside of an array. And then when we pull it out, we can convert it back to what we think it should be. But forget about that for right now. We do that more in the second class when we start talking about data structures. And the funny thing there is when I say data structures, it came from that guy. The idea of a struct. So this is the, if C is the great-grandfather of all our modern-day programming languages, structs are the great-grandfather of our modern-day programming paradigm. Is the great-grandfather of our modern-day programming paradigm. Fair enough. That'll make sense here what I'm going to say in a second. Okay, so structs solve a problem. But now we run into this situation. What if we want a fraction to be able to add itself to another fraction? Well, what we did today is we liked putting a add method in here, right? That did something. Structs didn't allow it. So what you would have to do as a C programmer, this is in the last days of when C was still popular, let's say. You would have to create your add method up here. That would take in a fraction f. This was called an add function, not a method. Methods didn't exist yet because object-oriented programming languages didn't exist yet. But, you know, it looks a lot like a method. But it was called a function. It's called a function because it returned a value. If it didn't return a value, it would be called a procedure. All right, so we write it up here. And then the C programmers figured out how to create this weird hack thing. Void pointer, add function, let's just leave it at that. So they would create this weird variable in here that would hold a pointer that allowed them to get to this function in their code. All right, so it was, how many of you have ever seen the show MacGyver? Okay, so 2 people. 2 people saw MacGyver. Yeah, you and her.
No.
I did not raise my hand. Look.
You saw MacGyver, didn't you?
I saw MacGyver. I think I did.
Okay. They don't have MacGyver in India, and you know what MacGyver is, don't you?
I think I've seen it, but I'm not good at movies.
It's not a movie; it's a TV show.
Yeah, I mean TV show.
Yeah. Okay, you've lost. So the punchline with MacGyver, we're all MacGyver as programmers, okay? Because we have to solve problems in terms of the tools we have available to us, right? Well, we're really all MacGyver all the time, just as humans. If we need to do something around the house, well, we got to look around and see what's available to us. If you're going to make dinner and you didn't go to the grocery store, you got to look at the fridge and see, A, what hasn't gone bad, Okay? And what technically should go with whatever else is in there. You know, there's certain things you just don't mix, you know, like orange juice and, I don't know, yogurt and eggs in a pan. In a pan. In a pan. Yeah, I was going somewhere with that. But in any case, we solve problems in terms of what we have available to us. Well, you looked it up, didn't you?
Yeah.
Okay. So MacGyver, actually the guy, he's, I think, more famous now for playing in Stargate SG-1, that TV series. But originally he was famous for MacGyver, where every single episode this guy got captured. And he'd be tied up in some garage somewhere or something, and he would build like an airplane out of like a broken lawnmower, a piece of rope, and some floss. You know, that was every episode. You know, he would make something impossible. Even Mythbusters have had you've seen Mythbusters, right? TV show? Mythbusters once had an episode that tried to determine whether some of the stuff that was on MacGyver was possible. You know, given the 2 or 3 things that you had, could you actually build and fly, you know, something that could fly and hold a human being? But in any case, these C programmers back then were kind of pushed up against the wall. They were in a situation where they had to learn how to solve a problem that the language wasn't designed to solve. Okay? Now remember, programming languages have the goal of letting human beings solve problems the way they solve them in real life, right? Now, C was a perfectly acceptable language for a very long time because the types of programs people were writing in C in the earlier days of C were far less complicated, far less complex than the programs they were writing in the later days. It's not so much that the programmers got smarter, it's that the capabilities of the computers got better. Our early computers could only do so much. So as our computers got more and more powerful, the types of things that our imagination allowed us to figure out how to do on them became more complex. We were asking more and more of our programming languages, right? So this is kind of where C hit a wall. It's like, wait a minute, you want to actually be able to call functions from within a struct? That's not part of the language. We didn't think you'd ever want to do that. Okay, but we just proved today that we think it's a decent idea, right? Decent idea. So, along comes C++. So this new language C++ came out, which was the object-oriented version of C. And you also had Objective-C. Apple, Microsoft. Actually, Microsoft came out with something called Visual C++. Which is just the C++ language that Microsoft could charge you for. It also had some widgets in it to allow you to build Windows applications. Let's see, where was I? All right, so then we had to move on to C++. And what C++ did for us added objects through the class keyword. Let's leave it at that. Added objects through the class keyword. So now what you could do is you could create a class called fraction, have a numerator denominator, and you could pull your add method now they're called methods because it's an object-oriented language, inside of that class, and now it was all self-contained. So this guy's starting to look like an object-oriented language now. Okay? So what a class is a struct that allows you to have methods inside of it, in simplest terms. Okay? Now, what did Java do? The next level of evolution, right here. Java said, we're going to get rid of structs. For starters, Why is that? Well, if this is a fraction, struct, this guy right here, isn't a struct actually just a class without methods in it? It's the same thing. Why do I need two different things to solve the same problem? If you only need to hold on to variables, fields, if you will, if you only need those, then don't put any methods in there. And you have a struct. Okay, so Java got rid of something called a struct, but they still exist through classes. All right? Now, one thing I might say in there, though, let's see, where am I going? I'm lost. Okay, here we go. So they got rid of structs, and we might say, because structs could be implemented using classes. But the catch there is that in C and C++, the two languages before Java, structs were always passed by value by default. So they were always primitive types. Objects in Java are always passed by address. Okay, we talked about this when we dealt with pointers. Passed by value versus passed by address. So now, if you want to represent the struct-like class of a fraction in Java, it just has a numerator and denominator but no fractions, or no methods rather. When you pass that around to different methods, it will get passed as a pointer, as an address. So any changes you make will be permanent changes. No big deal, as long as you know that's how it works. But if you were already a C and a C++ programmer and you were used to structs being passed around by value rather than by address, you knew that changes were not permanent. So you had to change your problem solving a little bit when you moved to Java and started saying, oh, well, this is the job for a struct. Oh, well, structs don't exist in Java, but I'll just build a class. It solves the same problem, but has a little caveat with it that makes you have to remember that classes are passed by address, not by value. All right? So Java got rid of structs. Java removed a lot of verbiage. We saw some of that today, right? We removed the whole extending object stuff, and a lot of stuff's hidden from us that we now know is there. Okay? And removed a specific syntax for pointers. And we've already talked about that. That in Java, some of the textbooks say pointers don't exist. The reality is in Java, everything's a pointer. So we don't have a specific syntax for it. All right? Okay. Questions about any of the stuff we've covered so far today?
So back to the days when struct was exist, so if you print a struct, what it will print out?
If you print a struct, what would it print out? I believe. Definitely not an address.
For example, like a struct of a fraction.
I think it had like a format, like it would have a curly brace and then the values separated by commas. I think. That's a good question. Let me see here real quick. %P. see what that shows. Oh.
Percentile D.
What'd you say?
Percentile D.
LD?
Oh, it's just D.
Instead of P, we should enter D.
Well, D is decimal.
D is for integers, right?
D is for
Yeah, but it's a struct. Why can't I? Oh, there we go. Yeah, F is a struct, not a decimal. Man, how do you print out a struct? Can you print out a struct directly? Yeah, see, this is the format I thought it was going to kind of have.
percentages.
Percentage S is for a string. That's the placeholder for a string. Char pointers are strings. Yeah, it's actually interesting. It looks like maybe there was not a specific way for printf to print out a struct. Because structs weren't meant to be displayed; they were meant to be to hold data. You could certainly write a function that would display the contents of a struct by doing a printf. The integer would be, you'd print out a %d for the integer. So for instance, I should be able to do something like this. F dot numerator. Oh, there's my one down here. So I could do, let me just get rid of this line real quick. So I can come in here, I could do slash %d, then \n to kick it down a line. So f dot numerator, f dot denominator. So there's the 1/2. Yeah, so it looks like you can't directly print a struct.
So my question is actually the elements inside the structure, they are storage together, in the memory or separate.
They'd be stored together, similar to an array. Yeah, it would be contiguous in memory, like an array. All right, that makes sense? Okay, questions, comments, concerns, bribes about any of the stuff we've talked about here so far? All right, well, let's take a break and come back in about 15 minutes or so.